probability distribution becomes easier by employing contingency tables. Contingency tables are also called crosstabs or frequency distribution tables, and their job is to summarize the relationship between the categorical variables involved in a research process. For example, a researcher may be interested in finding relationship between diabetes and eating preferences. Then diabetes and eating preferences will be the categorical variables involved, and the question could be, is there a significant relationship between diabetes and eating preferences? And then the researchers may run a chi-square test, which we will discuss at a later stage, to determine the exact relationship or the expected relationship between these two variables. Contingency tables are divided into cells and are notoriously important to determine the expected frequency of each cell. It can be created in Excel using the pivot table tool. And today we will create some contingency tables with simple examples that would develop your skills to take it further. So let's move on. Contingency tables provide information about the dependency of variables in a situation, and it helps examining the probabilities independently as well as dependently. You can see the table as a matrix with variables in rows and columns, and that helps you determine the probabilities of intersections, unions, and conditional probabilities. For example, table 3.3 shows a contingency table in which the rows represent the number of athletes who do stretches and those who do not stretch, while the number of columns represent the number of athletes who had injury in the last year and who did not have an injury in the last year. Please read this table carefully and see how the information is presented and what is the total number of stretches, athletes who stretched, whether they injured or not, what is the total number of athletes who did not stretch, whether they had injury or not. This is given in the last column, and the last row represents the total number of injuries, whether the athlete stretched or did not stretch, and also the number of no injuries, whether the athlete stretched or did not stretch. And the total number of athletes is the total number of elements in the rows and in the columns, and they turn out to be 1000. So please pause the video here and take a moment to understand and grasp the information in your mind. Now the question asks you, the first question is the probability that the athlete stretches before exercising. So you have to tell the probability that the athlete stretches, whether they had an injury or they did not have an injury. Now, can you tell me what should be the total number of athletes who stretched, whether they had an injury or not? I'm sure you say 550, because that will include the total number of athletes, whether they injured or not, who stretched. Okay, so the answer to this question, when they find the probability that the athlete stretched before exercising, is the number 500 out of the total number of athletes, which was 1000. The next question asks you to find the probability that the athlete stretches before exercising, given that no injury occurred. For this, you have to do some workout, and probably a good idea would be to make a tree from the given information in the contingency table that may help you find that information quickly. So we start constructing the tree diagram by constructing the starting points of S and NS, where S represents the number of athletes who stretched and NS who did not stretch. And both of these variables led to two more variables, injuries and no injuries, for both stretched and non-stretched athletes. And we also see that the total number of athletes who stretched were 550, and those who did not stretch were 450, while the number of athletes who were injured even after stretching was 61, and those who did not injure after stretching were 489. Similarly, the number of athletes who injured after no stretching were 231, and those who did not injure after not stretching were 219. And we are interested in finding the probability that an athlete stretched and he did not injure while he did not injure. So we also say that probability of athletes who stretched given that they were not injured. And we know that this is a conditional probability, and for that we have to compute the probability of the intersection of stretching and no injury and divide it by the probability of no injury. And we know that the intersection comes from the second row of the tree because there has been no injuries after stretching, and they were 489. While the total number of no injuries come from calculating all the number of athletes who did not injure, whether they stretched or did not stretch, and that comes as the sum of 489 and 219, which turns out to be 708. So we enter this figure 489 by 708 in our worksheet, in our actual worksheet, and we see how we went. 489 divided by 708, and we see how we go. Okay, both our answers are correct, so we formulated the right strategy to get the information that we required for this question using the contingency table. Now we see another interesting exercise where you'll be doing a bit more work than before. And we are looking at the weights and heights of a group of individuals who participated in an observational study. The rows of the table represent different weights, and the columns represent different heights. So you see that there are some overweight people with different tall, medium, and short heights, and then there are normal people and there are underweight people in the rows. And there is some information in the columns about the heights. So tall people have different weights, and then medium people have different weights, and short people have different weights. The totals have to be calculated, and then some more information has to be extracted from the intersections given in this contingency table. And we need to find the exact answers required in the table. So for example, we have to find the total of the first row, which represents obese people who are overweight, and 16 of them are tall, 25 of them are medium, and 13 of them are short. So the total number would be 54. Similarly, in the next column, the total number of people who were normal, including all tall, medium, short, was 99. And the third column, the total number of underweight people turns out to be 43. And now we need to do the column totals. So in the first column, we are computing a number of tall people, including all the overweight, normal, and underweight people, and that turns out to be 51. In the second column, there are medium people, and they turn out to 94. And the third column, we are computing all short people, and their total number is 51. And the grand total of all the rows and columns turns out to be 196. And now we are interested in finding the probability of tall people. Okay, now the probability of tall people would be the grand total of all the tall people, and that is 51 out of 196. So we enter 51 out of 196. And now we find the probability that a randomly chosen individual from this group is obese and tall. And we know that the word "and" represents intersection. So the intersection of obese and tall people in the contingency table is 16, obese and tall. So we enter 16 divided by 196. And then the probability that a randomly chosen individual from this group is tall, given that the individual is obese. And we know that we have to do some workout for this like before, and this time I am leaving it to you to do the workout. I am just entering the answer for you to verify if your workout is correct. Next we see another very interesting example in which we have 3 red balls and 6 yellow balls in a box. So altogether there are 9 balls. 2 balls are drawn from the box without replacement, which means that we draw 1 ball and then without replacing it we draw another ball. And we want to find the probability that 1 ball of each color is selected. Now we see that this information is very general, very primary, and we need to dig out some more information from here. So we go to our worksheet and do some workout. Start by choosing the balls at random, and if we choose a ball at random, it could be red or it could be yellow. So we start by making the tree diagram, taking each red and yellow as an option, and we know that the red ball has a probability of 3/9 and the yellow ball has a probability of 6/9 to be chosen in the first place. And each of these balls, after it is chosen, they have the chance of choosing a red and a yellow ball. So the second part of the tree would be choosing a red and a yellow ball when the red and ball are chosen in the first place. And since we are interested in choosing a ball of each color, this means that if we choose the red ball in the first place, the second option should be a yellow ball. Or if we choose a yellow ball in the first go, then the second grasp should be on a red ball. So we are only interested in 2 of these options. Okay, now in the first of the chosen option, if a red ball has been chosen in the first place, its probability is 3/9, and if the yellow ball is chosen in the second place without replacing the red ball, then its probability should be, I'm sure you said 6/8. Why? Because a ball has already been drawn and is not replaced. Okay, now similarly, if the red ball is chosen after the yellow ball, then there are 8 balls. Of these, all red balls are there, 3 of the red balls are there, so the probability will be 3/8. So if we want to know the probability that red and yellow balls are chosen, then this means that we want both of these options to occur, the ones that are circled. So we want the first option, which is the probability of the red and a yellow ball, which means that since yellow and red balls are independent events, their intersection would be the product of their probabilities. So 3/9 times 6/8. And similarly, for the second case, again, yellow and red balls have the same chance to be chosen in the first and the second place. So their intersection would be the product of their probabilities. So 6/9 times 3/8. And rest we do the calculations. So the first part gives us 18 on 72, and then the second part also gives us 18 on 72, and this gives us 36 on 72, which will turn out to be a half, isn't it? And so we need to answer the answer 1 by 2 here, and let's see. Okay, so our answer is correct, and I hope now you enjoyed this example and the strategy.